Every day, we measure temperature without giving it a second thought. A thermometer tells us whether we have a fever, whether our coffee is hot enough, or whether the weather is getting colder. But have you ever stopped to ask, how does a thermometer actually know the temperature of an object? How does a tiny glass tube, or a digital sensor, tell us something we can't even see? And here's an even stranger question. We've already covered the first, second, and third laws of thermodynamics in this series. So why are we now going back to learn a law called the Zeroth Law? Shouldn't 0 come before 1? Stick around, because by the end of this video, both of these questions are going to make perfect sense. But before we understand what the Zeroth Law actually says, we need to understand why it exists in the first place. And for that, we have to travel back to the history of thermodynamics. Here's the interesting part. The first, second, and third laws were all discovered and formally stated long before the Zeroth Law. But as scientists continued developing thermodynamics, they uncovered a hidden assumption that every one of those laws had been relying on from the very beginning. It was so fundamental that it logically belonged before the first law itself. Instead of renumbering the existing laws, scientists gave this newly recognized principle a rather unusual name, the Zeroth Law of Thermodynamics. To truly understand this law, we must first explore the concept that forms its foundation, thermal equilibrium. In fact, without understanding thermal equilibrium, the Zeroth Law is nothing more than a statement to memorize. Once you understand it, the law becomes surprisingly simple and explains something we use every single day, how a thermometer measures temperature. So, let's begin with a simple everyday example. Imagine placing a hot cup of coffee on a table in a room. Because of this temperature difference, thermal energy naturally flows from the hot coffee to the cooler surroundings. As the coffee loses thermal energy, its temperature gradually decreases. At the same time, the surrounding air gains a tiny amount of that energy. This process continues until something interesting happens. Eventually, the coffee and the surrounding air reach the same temperature. At this point, there is no net transfer of heat between them. This state is called thermal equilibrium. In simple words, thermal equilibrium is the state in which two objects in contact have the same temperature, so no net heat flows between them. Notice something important. Heat transfer doesn't stop because the particles stop moving. The atoms and molecules in both the coffee and the air are still constantly moving and colliding. Heat transfer stops because both objects have reached the same average kinetic energy, or in other words, the same temperature. But now, let's take this idea one step further. What if two objects never come into direct contact with each other? Can we still determine whether they have the same temperature? To answer that, imagine introducing a third object, which we'll call Object C. First, place Object A in contact with Object C, and wait until they reach thermal equilibrium. Then remove Object A and place Object B in contact with the same Object C. After some time, they also reach thermal equilibrium. Now comes the interesting question. If you bring Object A and Object B into direct contact with each other, will heat flow between them? The answer is no. Since Object A and Object C have the same temperature, and Object B and Object C also have the same temperature, Object A and Object B must already be at the same temperature, even though they were never directly in contact. As a result, no net heat flows between them. This simple yet profound observation forms the very heart of the Zeroth Law of Thermodynamics, which states, if two systems are each in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. Let's connect this with the example we just saw. System A reached thermal equilibrium with System C. System B also reached thermal equilibrium with System C. Therefore, according to the Zeroth Law of Thermodynamics, System A and System B must also be in thermal equilibrium with each other, even though they were never placed in direct contact. At first glance, this statement might seem almost obvious, but its importance goes far beyond that. This simple principle gives us the very foundation of temperature as a measurable and comparable physical quantity. It tells us that temperature is the property that determines whether two systems will be in thermal equilibrium. If two systems have the same temperature, no net heat flows between them. If their temperatures are different, heat naturally flows from the hotter system to the colder one until thermal equilibrium is reached. And this is exactly the principle that makes thermometers possible. Let's see how. Imagine you have a thermometer at room temperature, and you place it into a cup of hot coffee. At first, the thermometer and the coffee are at different temperatures. Because of this difference, heat flows from the hotter coffee into the cooler thermometer. As the thermometer absorbs thermal energy, its temperature begins to rise. This exchange of heat continues until the thermometer and the coffee reach thermal equilibrium. At that moment, both have the same temperature, and no net heat flows between them. The thermometer doesn't detect temperature directly. Instead, it reaches the same temperature as the object and then displays that temperature using a physical property that changes predictably with temperature. For example, in a mercury thermometer, the mercury expands and rises inside the glass tube. In a digital thermometer, an electronic sensor changes its electrical resistance, which is converted into a temperature reading. Different thermometers use different physical principles, but they all rely on the same fundamental idea. They must first reach thermal equilibrium with the object being measured, and that is only possible because of the Zeroth Law of Thermodynamics. Without this law, we would have no reliable way to compare temperatures or calibrate measuring instruments. Every time you check your body temperature, measure the temperature of your food, or monitor the temperature of an engine, you're witnessing the Zeroth Law in action. Every temperature measurement we make is based on the Zeroth Law of Thermodynamics, which allows one object to accurately measure the temperature of another. It is the silent, invisible principle that makes every thermometer and every temperature measurement possible. Let's take a moment to look back at everything we've uncovered throughout this video. 1. The Zeroth Law earned its unusual name because it was discovered after the other laws, yet it forms the logical foundation on which they all depend. 2. Thermal equilibrium is the state in which two objects in contact have the same temperature, so there is no net flow of heat between them. 3. The Zeroth Law of Thermodynamics states, if two systems are each in thermal equilibrium with a third system, then they are also in thermal equilibrium with each other. 4. This simple but fundamental principle makes temperature a measurable physical quantity and provides the scientific foundation for every thermometer we use. And with that, we've completed our journey through the 4 fundamental laws of thermodynamics. From the Zeroth Law, which gives us the foundation for measuring temperature, to the third law, which reveals the fascinating concept of absolute zero, each law answers a different question about how nature works. Together, they form the foundation of classical thermodynamics. If this series helped thermodynamics finally make sense, I'd love to hear from you. Let me know in the comments which law fascinated you the most. If you enjoyed the series, don't forget to like the video, subscribe to Decoding Education, and turn on notifications so you don't miss our upcoming science videos. I'll see you in the next episode. Until then, keep decoding.